So you guys did this lab yesterday where you had to place a whole bunch of different masses on a meter stick and then record the forces that each sensor read. And I don't have the exact numbers, but I'm guessing you had like 4.33 and maybe 1.2. And then you added 250 grams at 1 centimeter, and this one I think went to like 5.7, and this one maybe went to 0.42 or something. And then you added one more 250 gram mass, and this one maybe went to 6.2, and this one maybe went to 1.1. I don't know. I don't know what the numbers were. But I do know the right general pattern, right? How did the forces change when the first 250 gram mass was added? Okay, so you look at this and you go, okay, so we added one 250 gram mass, and the left sensor reading, this one increased. Okay. The right sensor reading should have decreased. Okay. Now, why did that happen? I want you to think about that. And for this, I'm going to need to draw a picture. So my meter stick was right here. I had one sensor hooked up to it pulling up over here. I have another sensor over here pulling up. And we put a big heavy mass right here. It pulls down. Okay, and then we added another little mass right here. It also pulls down. So why does adding a mass that pulls down on it only cause one increase in force? Well, if you think about it, okay, this downward force right here, yeah, this sensor has to pull against it, but because this meter stick is fixed right here, what this force does is it tries to rotate this end down, which causes this end to rotate up. Okay, so this one, there's more weight to support, but on the right sensor, there's less weight to support because of a rotation that's tried to happen. Okay, then you added that second 250 gram mass, and both of these should have increased. Okay, and the reason for that, well, let's take a look at our picture again, right? If I add a force right here, okay, then yeah, it pulls down on this one and it pulls down on this one because it's in between them. Okay, it doesn't matter where I put my rotation. This is trying to rotate it this way, trying to rotate it this way. Okay, so both the sensors have to pull up because of the weight pulling down. It's not causing the rotation like the other one was. Okay, now, did adding mass to the meter stick cause any acceleration or rotation? It shouldn't have, right? The meter stick just basically hung there in the force probe the whole time, so no. And if that's the case, if there is no acceleration or rotation, what can we say about net force and net torque? Net force must be 0, and net torque must be 0. If this wasn't the case, then the thing would have accelerated or rotated. Alright, it says draw a free body diagram of the system below. So here's my meter stick. I've got the left sensor pulling up, I've got the right sensor pulling up, I've got the 550 grams pulling down, the 250 grams pulling down, and the 250 grams pulling down. So there it is. Now, because torques cause rotations, right, or angular acceleration, we need to choose an axis of rotation. You can choose any point. It doesn't matter. Mathematically speaking, it all works out the same. But if we choose the left side sensor to be our axis of rotation, then this force right here doesn't cause any torques because it's got no lever arm. Okay, so for now we're going to choose this side, that location, to be our axis of rotation. Okay. Now that you have an axis of rotation, you can calculate lever arms, find the lever arm for each object, and record it in the table. Okay, so lever arm is the distance from the axis of rotation to where the force actually acts, right? So when you have their 550 grams, it was added at 30 centimeters, but your left side sensor was at 20 centimeters. So from 20 to 30 centimeters is 10 centimeters, but this says meters, so that's 0.1, right? Your 250 gram mass at 1 centimeter, 1 to 20 is 19 centimeters, or 0.19. And your 250 grams at 70, 20 to 70 is 0.5 meters. Alright, next up we have to calculate force that results from each mass. Well, 550 grams, okay, is the same as 0.55 kilograms. And to get the force that it gets, it's just mg, right? It's the weight. So kilograms times 9.8, and I think that's 4.3 something something. I don't know. It must be 5 point something. Okay. Anyways, you get that, and you'll get a force here, force here, and a force here. So basically, you just take 0.55 times 9.8, 0.25 times 9.8, 0.25 times 9.8, and you get your forces. Okay, and then it says, all right, now we need to calculate torque. Well, remember, torque is force times lever arm. Okay, so you have a lever arm in this column, you have a force in this column. You can just multiply these two things together and you'll get a torque. Direction is important. Okay, if you look, your 550 gram mass is this one right here. Right? Here's my axis of rotation. It's causing this thing to try to rotate, but it's trying to cause it to rotate in a clockwise direction. Okay, so whatever you get, this one's clockwise. This one, this 0.19, it's over on this side. It's trying to get this thing to rotate this way. That's counterclockwise. Okay, and this one's clockwise again, because it's this one over here. It's trying to rotate it this way. Now, why does that matter? Well, clockwise and counterclockwise are going to pull against each other. So on the next question it says, okay, find your net torque. Well, net torque is the sum of the torques, but you're going to have torque 1 minus torque 2 plus torque 3. And the reason for that is because this torque in the middle, right, the one from that first 250 gram mass, tried to go against these two. Whatever that is, that's your number. Now, what direction is that going to be? Well, it depends, right? If it's positive, then I think I just said, since I got to go back and look, right? Since torque 2, since this one I said was negative, okay, I just assigned counterclockwise to be negative. Okay, so if this is negative, it's counterclockwise. If it's positive, then it's a clockwise torque. Okay, since the net torque must be 0, there must be another object or objects exerting a torque. Which other objects are exerting the torque? Well, let's go back and look at our sensor, our diagram. Okay, we accounted for the torque of this thing, we accounted for the torque of this one, and we accounted for the torque of this one. This is my axis of rotation, so this sensor has no lever arm, but this sensor, the right side sensor, it does. Okay, so this thing is pulling up, which actually is causing a torque. And it's a counterclockwise torque. It is pulling up and left against the axis of rotation. Okay, and so the right sensor exerts this torque. Okay, based on your answer to number 9, what is it? Well, it has to be exactly equal and opposite, right? Because this thing isn't accelerating, it isn't moving, it's in equilibrium. Okay, so whatever this is, it's equal but opposite. Now, 11 says, okay, use the force data on page 1 to calculate torque caused by the right sensor. Alright, so if I go all the way back to page 1, okay, you have a table that has the force reading for this right side sensor, and we want it with all the masses on there, so we go find this, okay, whatever it is, and now I'm actually going to go to this other table. Okay, and the object that we have is the right side sensor. Okay. Its lever arm, well, it's at 90 centimeters. This thing, the left sensor, our axis of rotation is at 20, so that's 0.7. Its force is whatever we just pulled out of that table at the front, and then your torque, you just take your force times your lever arm and you put it right here. Okay. Now, whatever that is, you can show me that again. So 0.7 times, I think 1.1 or whatever it was. I don't know what your numbers were. Okay. This would be 0.77 Newton meters, and since this is pulling up in this way, that's a counterclockwise torque. Okay, 12 just says, okay, how does this value that you calculated right here compare to this value that you thought it should be up there? They should be fairly close. Alright, so what do we get out of this lab? 1 is static equilibrium. You built a system in static equilibrium. Okay, the net force and net torque were both 0, and it does not undergo linear angular acceleration. Not only is that true, but also in static equilibrium, that means that it's not accelerating, but also the velocity and the angular velocity are also 0. Okay, so it's not accelerating and it's not moving. Center of mass. Okay, this is another little one, and this didn't really come out in the lab, but I cheated at the beginning. I had you zero the force probes after you had already put the meter sticks on there, after you had already hung the weight hangers on there. Okay, and so the reason I did that is because the mass and weight of the meter stick is actually going to cause some rotation and make some things move, okay, and cause some forces, and I didn't want those to mess with us. But think about this: if you have a meter stick, just the meter stick suspended, and this thing's pulling up and this thing's pulling up. Okay, let's say this is my axis of rotation. This one doesn't have any torque on it because the axis, okay, but where's the mass of the meter stick? Okay, well, because the mass is distributed equally along the meter stick, that's a very hard question to ask, right? Each point on this meter stick would exert a torque, but only at the mass at that point. Okay, well, how do you find mass at a point? You don't. Okay, but if you think about it, there is one spot on a meter stick where you could hold it and it would balance exactly, right? It's like where do you put the pivot to balance a teeter-totter? You put it right in the middle. That's called the CG, center of gravity or center of mass. Okay, and it's the balance point. And the cool thing about that point is it acts like all the mass is right there. So instead of saying we have to calculate the mass at every point, what we do is we say, oh, well, the axis of rotation to the center of mass is the lever arm. And that way we can deal with that torque in one spot. Okay, and that's sort of what this problem right here is getting at. Okay, so the last problem on this lab is actually kind of a complex problem, but it's a lot like what you just did in lab. Okay, so it says we've got a plank that has a mass of 10 kilograms that's resting on two sawhorses, and we want to figure out how much force each sawhorse has to exert to hold this plank up. But to complicate matters, there's also a 20 kilogram box of nails sitting right here. So this thing's 20 kilograms, this thing is 10. Okay, what are you going to do? The very first thing you need to do in any of these situations is pick, well, alright, I guess the very first thing we should do is we should probably label all our forces. Okay, I'm going to call this sawhorse A and I'm going to call this sawhorse B because I'm creative like that. That means sawhorse A is pushing up on the board, and so this is FA. Okay. Sawhorse B is also pushing up on the board, so this is FB. Now, those are not going to be equal because this box of nails is closer, the board's not centered. Okay, so each sawhorse doesn't exert the same amount of force. Then let's label our downward forces. Okay, the board actually exerts a downward force. Okay, so I'm going to call this, I guess I'm going to call it mg of the board, so mgb, and this is the nails, so mg of the nails, just so we know they're different. Now, here's what I can say. I can say the net force is FA plus FB minus MGA, or MGB, I guess, minus MGN, and that equals 0. Okay. Now I know MGB and MGN. I can find them. That's just 10 times 9.8, which is 98, and 20 times 9.8, which is 196, right? So there they are. There's my two forces down, which means my total net force up, FA plus FB, has to equal 196 plus 98, which is 294, right? So 294 newtons. That has to be the total force up to keep this thing from accelerating. But these things don't exert equal forces. Okay, the easiest way to do this problem, I think, is to put your axis of rotation on one of the sawhorses or the other. It doesn't really matter. I'm going to put one there. And then go to your net torque. Okay, and so the torques that each force cause, FA doesn't cause a torque because it's got no lever arm. See how tricky that is? Now, the board does have a torque. It's trying to rotate this way. It's okay, so this is a clockwise torque, and we're just going to go ahead and have our clockwise torques be positive. Doesn't matter as long as you keep everything the same. Okay, so the board has a clockwise torque. Now the total board is 7 meters long, which means this thing right here, where it actually pulls down, that 1 and 3 is 4, 5. Okay, yeah, I did that right. That's 3.5 meters. That's the center of mass. So the torque from the board, its lever arm is 3.5 meters, and its force is 98. So 98 newtons is my force times its lever arm, 3.5. That's a clockwise torque. Okay, plus I have another clockwise torque. I have this box of nails. Okay, this box of nails is 3 meters from. Oh, I better be careful. right there, that's the distance from the edge of the board, not from my axis of rotation. Okay, so it's not 3.5 meters. 3.5 meters is to the middle of the board, but since this starts 1 meter in, this is only 2.5 meters. Okay, sorry about that. All right, plus my box of nails, it's also causing a clockwise torque. It's trying to pull this board down. Okay, it's got a force of 196 newtons and a lever arm of, from here to here, that is 3 meters. Okay, and then finally, I'm going to subtract off this torque, right? The whole thing is prevented from rotating by the second sawhorse, whatever it is. It's got a force B, okay, and a lever arm of 4 meters. Okay, and I know that the net torque has to equal 0 because this thing is in static equilibrium. It's not accelerating, it's not rotating. Okay, so then you can do the math. 9.8 times, or 98 times 2.5, 196 and 49 is 245. I think that's right. I'm not really sure. 196 and 49, I think, yeah. Okay, don't know. Plus 196 times 3, 3 times 6 is 18, 3 times 9 is 27, 28, and 3 times, okay, 588, minus 4FB equals 0. Okay, well now you're about done, because 588 plus 245, 5 and 8 is 3, 4 and 8 is 3, 5 and 2 is 8. Okay, 833 equals 4FB. Technically, I suppose I added this over, so we're good. So I divide by 4, and I get, gives me 8, remainder 2, 5, not 1525. Anyways, 208.25, something like that. That's the force from FB. Then you can go back up into this equation and figure out how much force this sawhorse actually has to exert, and it's going to be the difference, right? So you subtract that off, and it's like 86 newtons or something like that. 87.75, I don't know. Okay, but all you got to do is find your torques and forces, add them up, set them equal to 0, everything works out. Okay. There will be a couple problems I need you guys to do today. If you have questions, email me or come see me.